Look up at the night sky. What do you see? A scattering of stars, the faint glow of distant galaxies, maybe the streak of a passing comet. But what if I told you that beyond the familiar lies a universe teeming with cosmic oddities so bizarre they make black holes look ordinary? We live in a cosmos that's far stranger than we've been taught, filled with colossal structures and mysterious phenomena that defy the very laws of physics as we know them. From galaxies that shouldn't exist to voids so empty they unsettle astronomers, the universe is hiding secrets that rewrite our understanding of reality itself. Think about this for a moment. Everything we see, the planets, stars, even the Milky Way, makes up less than 5% of the universe. The rest, dark matter, dark energy, and cosmic puzzles we're only beginning to unravel. And nestled within that unknown are structures so vast, so peculiar, they've left scientists scratching their heads for decades. Imagine a ring of galaxies stretching billions of light years across, or a cosmic dead zone where nothing seems to exist. These aren't sci-fi concepts, they're real, they're out there, and they're waiting to be explored. That's exactly what we're diving into today. Over the course of this journey, we'll uncover 25 of the most mind-bending cosmic structures ever discovered, each one a testament to how little we truly know about the universe. Some challenge the limits of gravity, others hint at forces we can't yet explain, and a few might even rewrite the story of how everything came to be. So if you're ready to venture beyond the textbooks and into the cosmic unknown, stick around, because by the time we're done, you'll never look at the night sky the same way again. The first cosmic oddity on our list isn't just strange, it's downright unsettling. Lurking in the direction of the Centaurus constellation, there's something with enough gravitational might to yank entire galaxies off course, including our own Milky Way. Scientists call it the Great Attractor, and it's one of the most baffling phenomena in modern astronomy. Picture a cosmic whirlpool, invisible yet powerful enough to bend the paths of thousands of galaxies toward it at mind-blowing speeds. But here's the catch, we can't even see what's pulling us. Our own galaxy's dense core blocks the view, shrouding this gravitational monster in mystery. What makes the Great Attractor so perplexing isn't just its hidden location. The sheer scale of its influence defies expectations. Based on the motion of nearby galaxies, astronomers estimate its mass could be equivalent to tens of thousands of Milky Ways packed into a region of space roughly 400 million light-years across. That's enough raw gravitational power to reshape entire swaths of the universe. Yet, when telescopes peer in its direction, they don't find a single supermassive object, just a diffuse sprawl of galaxy clusters, far too sparse to explain the pull. Some researchers suspect an even larger structure, like the colossal Vela supercluster, might be lurking behind it, amplifying the effect. Others wonder if dark matter, that invisible cosmic scaffold, is woven into an unseen configuration here, warping space-time in ways we don't yet understand. The more we learn, the deeper the mystery grows. In the 1980s, when astronomers first noticed galaxies drifting unnaturally toward this patch of sky, it upended assumptions about how matter is distributed in the universe. It hinted that there might be structures, vast, invisible frameworks governing cosmic motion on scales we'd never imagined. Today, the Great Attractor remains a humbling reminder. Even with our most advanced tools, the universe keeps its most profound secrets just out of sight. And that's just the first stop on our tour of cosmic enigmas. But if the Great Attractor represents a cosmic anomaly with too much gravity, the Boots void is its polar opposite, a staggering emptiness where almost nothing exists. Spanning an incomprehensible 330 million light-years, this region of space is so devoid of galaxies that astronomers often call it the Great Nothing. To put that into perspective, if you place the Milky Way at one edge of the void, you'd need to travel the distance of over 3,000 Milky Ways laid end to end before finding anything of substance on the other side. In a universe teeming with galaxies, this gaping hole is eerily quiet, challenging everything we thought we knew about how matter is distributed across the cosmos. What makes the Boots void so baffling isn't just its size, it's the sheer improbability of its existence. According to our best models of cosmic structure formation, matter in the universe should clump together in a roughly uniform way, like foam on an ocean wave, with filaments of galaxies separated by modest voids. But the Boots void isn't just a gap, it's a cavern so vast that it defies even those generous expectations. Imagine stirring a spoonful of sugar into your coffee and finding, against all odds, a single area where not a single crystal dissolved. That's the level of statistical weirdness we're dealing with here. When astronomer Robert Kirshner first stumbled upon the void in the 1980s, his team expected to find at least a few thousand galaxies based on prevailing theories. Instead, they counted barely 60, a cosmic ghost town where there should have been a metropolis. Some researchers speculate that smaller voids might have merged over billions of years, creating this colossal emptiness. Others suggest dark energy's repulsive force could have aggressively pushed matter away, but even these explanations feel inadequate when faced with the void's staggering scale. Here's where it gets even stranger. The few galaxies that do cling to life inside the Boots void aren't like their neighbors elsewhere in the universe. Isolated and starved of interactions, they've evolved in bizarre ways, with some showing unusual structures or stunted growth. It's as if the void isn't just empty, it's actively altering the rules for anything trapped within it. This giant blank spot in the cosmic ledger forces us to confront an uncomfortable truth. Our maps of the universe might be missing fundamental pieces. If structures like the Boots void can exist, what other irregularities are lurking in the darkness, waiting to upend our understanding? Just when we thought we'd encountered the limits of cosmic scale, the universe unveils something even more staggering: the Hercules-Corona Borealis Great Wall. This mind-numbing structure isn't just large, it rewrites the rulebook for how we perceive the universe's architecture. Picture a colossal tapestry of galaxies, so vast it stretches across a tenth of the observable universe, over 10 billion light-years from end to end. To put that into perspective, if you could travel at the speed of light, it would take you longer to cross this single structure than the current age of planet Earth. What makes the Great Wall so revolutionary isn't just its size, it's the direct challenge it poses to one of astronomy's foundational ideas, the cosmological principle. This principle states that, on large enough scales, the universe should appear roughly uniform, with matter distributed evenly like sprinkles in a well-mixed cupcake. But the Hercules-Corona Borealis Great Wall throws that assumption into chaos. Here, galaxies aren't sprinkled, they're woven into an immense, lopsided filament, a cosmic thread so dense and sprawling that it defies the very notion of uniformity. Discovered in 2013 by a team analyzing gamma-ray bursts, the brightest explosions in the universe, this structure wasn't spotted through traditional telescopes. Instead, researchers noticed an unusual clustering of these bursts, tracing the outlines of something far larger than anyone expected. Gamma-ray bursts act like cosmic breadcrumbs, marking the locations of massive star-forming galaxies, and when mapped, they revealed this monstrous wall lurking in the shadows. The implications are profound. If structures like this exist, our understanding of the universe's large-scale structure might be fundamentally incomplete. Some theorists suggest such formations could only arise from irregularities in the early universe's density, flaws in the fabric of space-time frozen into existence during the Big Bang. Others speculate that unknown forces, perhaps even quirks of dark energy, could be sculpting these unimaginably vast formations. But perhaps most unsettling is the possibility that the Hercules-Corona Borealis Great Wall isn't alone. Could there be even larger structures waiting to be discovered, lurking just beyond the limits of our current observations? Each time we push the boundaries of our telescopes, the cosmos seems to respond with yet another enormity we never saw coming. If the Hercules-Corona Borealis Great Wall stretched our understanding of cosmic scale, the Sloan Great Wall smashes through those limits entirely. Discovered in 2003 by the Sloan Digital Sky Survey, this behemoth isn't just a collection of galaxies, it's a sprawling metropolis of cosmic structure, stretching nearly 1.4 billion light-years across. That's roughly 1/60th the diameter of the entire observable universe, a scale so immense it could contain tens of thousands of Milky Ways lined up end to end. But what truly sets this wall apart isn't just its size. It's the way its very existence nudges the boundaries of what modern cosmology says should be possible. At its core, the Sloan Great Wall is a filament, a thread of galaxies, gas, and dark matter woven together by gravity, forming one of the universe's largest known superstructures. Picture a spiderweb spun on a galactic scale, with strands of galaxy clusters intersecting at nodes so dense they resemble cosmic cities. But unlike the Hercules-Corona Borealis Wall, which revealed itself through gamma-ray bursts, the Sloan Great Wall was mapped directly through painstaking observations of galaxy positions. The Sloan Digital Sky Survey spent years cataloging millions of celestial objects, and when researchers stitched that data together, this gargantuan pattern emerged from the noise. Here's where the puzzle deepens. According to the standard model of cosmology, structures this vast shouldn't exist. The model, often called lambda CDM, predicts that matter should distribute itself relatively evenly across the universe, with only modest variations in density. Think of it like a balloon inflating. While there might be slight wrinkles, you wouldn't expect a single massive crease spanning a significant fraction of its surface. Yet the Sloan Great Wall does exactly that, presenting a density fluctuation so extreme it forces scientists to reconsider their assumptions. Some theorists argue this could be a statistical fluke, an unlikely but not impossible clustering of matter. Others suggest our understanding of dark energy's role in shaping cosmic structures might need revising. If dark energy's repulsive force isn't as uniform as we've assumed, it could have accelerated matter into these bizarre, sprawling formations. There's even a more radical possibility. The Sloan Great Wall might hint at primordial irregularities in the early universe, relics from the first moments after the Big Bang that never fully smoothed out. What's undeniable is the wall's impact on astronomy. It's not just an object of study, it's a challenge, a cosmic anomaly demanding an explanation. Every time we peer deeper into the universe, structures like the Sloan Great Wall remind us that the cosmos is stranger, more complex, and more wondrous than our theories can yet account for. And if history is any guide, the next great discovery might be lurking just beyond the edge of our current maps, waiting to rewrite the rules once again. Now let's shift our gaze from the visible to the barely detectable, a shadow in the afterglow of creation itself. In the cosmic microwave background, that faint echo of the Big Bang, astronomers have found something chilling, literally. Dubbed the cold spot, this mysterious patch of sky is colder than its surroundings by a tiny but statistically impossible margin. At first glance, a fractional temperature dip might not sound dramatic. But in the ultra-smooth backdrop of the CMB, where variations are measured in millionths of a degree, this anomaly stands out like a frozen thumbprint pressed into the fabric of space-time. The cold spot's existence throws a wrench into our understanding of cosmic evolution. According to standard cosmology, temperature fluctuations in the CMB should be random and relatively even, like static on an old television. But this region, spanning nearly 2 billion light-years, defies those expectations with its pronounced chill. Early explanations pointed to a supervoid, an enormous, empty region of space where the lack of matter could subtly cool light passing through it. But when astronomers scanned the area, they found only a modest underdensity of galaxies, nowhere near enough to account for the temperature drop. That's when things got interesting. Some theorists proposed a far more radical idea. The cold spot might be evidence of a collision with another universe. In the multiverse hypothesis, our cosmos isn't alone. It's one bubble in an infinite froth of universes, each with its own physical laws. If a neighboring universe had briefly brushed against ours in the distant past, the energy drain from that encounter could have left behind this cosmic bruise. It's a staggering idea, suggesting we might literally be seeing the imprint of another reality. Yet even this exotic explanation has its critics. Simulations show such collisions would likely leave more complex patterns than the cold spot's simple chill. Others argue the anomaly could stem from rare but not impossible statistical noise, a cosmic roll of the dice that landed on an unlikely outcome. But with odds estimated at 1 in 50 that such a fluctuation would arise naturally, the cold spot remains stubbornly enigmatic. What's clear is this: whether it's a sign of new physics, a glimpse beyond our universe, or just a statistical fluke, the cold spot forces us to question how well we truly understand the cosmos. And in that uncertainty lies the thrill of discovery, the chance that even in the oldest light we can observe, there are still secrets waiting to be uncovered. Stretching across the night sky like a cosmic smile, the giant arc is one of the most perplexing structures ever detected. A graceful curve of galaxies so vast it seems to mock our understanding of the universe's architecture. Discovered in 2021 by astronomer Alexia Lopez while analyzing light from distant quasars, this formation spans an astonishing 3.3 billion light-years, making it one of the largest single entities ever identified. To grasp its scale, consider this: if you could teleport to one end of the arc, the other would still lie beyond more than 30,000 Milky Ways placed end to end. But what truly unsettles scientists isn't just its size. It's the way this celestial crescent violates a fundamental rule of cosmology. The giant arc's existence clashes head-on with the cosmological principle, the long-held assumption that matter should distribute itself evenly across the universe when viewed at sufficiently large scales. Think of it like stirring cream into coffee. No matter how much you mix, there shouldn't be a single, unbroken swirl spanning half your mug. Yet that's precisely what the arc represents: a coherent, crescent-shaped concentration of galaxies, galaxy clusters, and gas clouds, all aligned in a structure that defies the odds. When Lopez first spotted the pattern in quasar absorption lines, shadows cast by intervening matter, even she questioned whether it could be real. But repeated analysis confirmed it. The universe had drawn a line in the cosmic sand, and we'd just noticed. Here's where the mystery deepens. Current simulations of cosmic evolution struggle to explain how such a colossal, symmetrical structure could emerge naturally. After the Big Bang, matter should have clumped into a web-like distribution, with dense nodes connected by filaments not organized into sweeping curves rivaling the size of the observable universe itself. Some theorists speculate the arc might be a remnant of primordial sound waves rippling through the early universe, frozen into the distribution of matter like a fossilized echo. Others propose more radical ideas, like exotic physics governing dark matter's behavior or even flaws in our understanding of gravity itself. What's equally fascinating is how the giant arc forces us to rethink our place in the cosmos. Unlike distant anomalies, this structure lies relatively close by in astronomical terms, just 9.2 billion light-years away, meaning we're seeing it as it existed when the universe was barely half its current age. If such immense irregularities exist within our observational horizon, what does that say about the universe's true structure beyond what we can see? The arc doesn't just challenge theories, it hints that the cosmos might be far lumpier, far more asymmetrical than we ever dared imagine. And perhaps most intriguing of all is the timing of its discovery. In an era where we've mapped millions of galaxies and probed the afterglow of creation, the giant arc emerged not from some cutting-edge space telescope, but from reanalyzing decades-old quasar data. It's a humbling reminder that the universe hides its grandest designs in plain sight, waiting for us to look and think differently. While we've explored cosmic structures that bend our understanding of space and matter, nothing prepares us for the dark flow, an eerie, unexplained current sweeping entire galaxy clusters toward something we cannot see. Picture hundreds of massive galaxy clusters, each containing thousands of galaxies, all drifting in the same direction like leaves caught in a cosmic river. This isn't just random motion, it's a coordinated movement so precise that astronomers have calculated speeds exceeding 2 million miles per hour, all aimed at a single point beyond the edge of our observable universe. The discovery of the dark flow sent shockwaves through cosmology when it was first identified in 2008. Researchers studying the cosmic microwave background noticed something peculiar. Galaxy clusters weren't just moving apart due to the universe's expansion, they showed an additional, unexpected velocity. It was as if an invisible hand were tugging them toward some distant, unseen mass. What makes this phenomenon so unsettling is that the source of this gravitational pull lies beyond our cosmic horizon, the boundary beyond which light hasn't had time to reach us since the Big Bang. In other words, whatever's causing this motion exists outside the realm we can observe or measure directly. But how could something outside our universe exert such influence? One jaw-dropping theory suggests the dark flow might be evidence of a neighboring universe brushing against ours. In the multiverse scenario, other cosmic bubbles could exist alongside our own, each with its own physical laws and structures. If one of these universes happened to pass close enough, its gravitational pull might ripple into ours, tugging at galaxy clusters like a magnet. Critics argue this explanation ventures too far into speculation, but the mathematics surprisingly holds up. The gravitational influence of a nearby universe could theoretically produce exactly the kind of motion we're witnessing. Alternative explanations aren't any less mind-bending. Some researchers propose that the dark flow stems from irregularities in the very fabric of space-time left over from the Big Bang. Imagine the early universe as a sheet of crumpled paper. Even if it expanded and smoothed out, some of those original wrinkles might remain, creating gravitational gradients that nudge matter in specific directions. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, might not be as uniform as we assume, generating unexpected currents in the cosmic ocean. What's undeniable is the dark flow's challenge to one of astronomy's core tenets, the cosmological principle. If matter and energy are distributed evenly on large scales, why would galaxy clusters exhibit such coordinated motion toward a single, unseen attractor? Either our understanding of the universe's structure is incomplete, or there's something fundamentally new waiting to be discovered just beyond the limits of our vision. Perhaps most tantalizing is the possibility that the dark flow isn't alone. If this phenomenon exists, could there be other invisible currents coursing through the cosmos, each hinting at realms we've yet to imagine? As telescopes grow more sensitive and our maps of the universe more detailed, we may find that what we call the universe is merely one thread in a far grander tapestry, one whose full pattern we're only beginning to trace. What if our entire cosmic neighborhood, the Milky Way, and everything around it is floating in an immense bubble of nothingness? That's the startling possibility raised by the KBC void, a colossal underdense region named after astronomers Keenan, Barger, and Cowie, who first identified it in 2013. Unlike the Boots void's eerie emptiness, this structure hits closer to home literally. Our galaxy sits near its center, tucked inside a region of space that's 20% emptier than the surrounding universe. The KBC void stretches an astonishing 2 billion light-years across, making it the largest known cosmic void relative to its observer. And its existence isn't just a curiosity, it's a direct challenge to one of astronomy's oldest assumptions, the Copernican principle. For centuries, we've operated under the idea that Earth, and by extension, our galaxy holds no special place in the universe. The Copernican principle insists there are no privileged observers. The cosmos should look roughly the same from any vantage point. But the KBC void turns that notion on its head. If we're sitting inside one of the universe's most significant underdensities, it means our local view might be profoundly skewed. Imagine living in a valley surrounded by mountains. Your perspective wouldn't reflect the broader landscape. Similarly, our measurements of cosmic expansion, dark energy, even the Hubble constant, could be distorted by this vast, invisible bubble we call home. Oddly enough, the KBC void might solve one mystery while creating others. For years, astronomers have wrestled with discrepancies in measurements of the universe's expansion rate. Different techniques yield conflicting results, a problem known as the Hubble tension. But if we're inside a void, the lower local density could explain why some measurements appear off. Gravity behaves differently here, with less matter tugging on galaxies, causing them to recede slightly slower than expected. It's like being in a room with weak gravity. Everything inside would behave just a bit differently than the outside world. Yet the void's sheer size raises eyebrows. Standard cosmological models allow for small underdensities, but one this massive pushes the limits of probability. Some theorists argue it could be evidence of exotic physics, like dark energy fluctuating in strength across space. Others suggest it might be a rare statistical fluke, a cosmic roll of the dice that landed us in an unusual spot. But there's a third, more provocative possibility. What if the KBC void isn't alone? If similar voids exist elsewhere, the Copernican principle might need revising, not discarding, a tweak to account for larger scale inhomogeneities we're only beginning to map. What's certain is this: the KBC void forces us to confront how much our cosmic address shapes our understanding of the universe. From our bubble's edge, the cosmos looks one way. But step outside and the view might change entirely. It's a humbling thought that even after centuries of stargazing, we're still learning how much the universe can hide in plain sight, especially when we're sitting right in the middle of the mystery. Forget everything you thought you knew about our cosmic address. The Milky Way isn't just some random galaxy drifting through space. We're part of something far grander, a structure so vast it redefines the meaning of home in the cosmic sense. Welcome to the Laniakea supercluster, a gravitational metropolis spanning 500 million light-years and containing roughly 100,000 galaxies, all bound together in an intricate cosmic dance. The name, from Hawaiian meaning immeasurable heaven, couldn't be more fitting. This is where our galaxy truly belongs, hurtling through space not as an isolated island, but as part of an immense celestial archipelago. Imagine the universe as a network of rivers with galaxies flowing like leaves caught in a current. That's precisely how astronomers mapped Laniakea, not by cataloging galaxies in static positions, but by tracking their motion through space. Using advanced radio telescopes to measure cosmic velocities, researchers noticed something astonishing. Nearly every galaxy in our neighborhood, including the Milky Way, flows toward a single gravitational focal point they dubbed the Great Attractor, a different phenomenon than the one we discussed earlier. These converging paths revealed the supercluster's true boundaries, drawn not by arbitrary lines but by the irresistible pull of gravity itself. At the heart of Laniakea lies the Norma cluster, a dense knot of galaxies acting as the supercluster's gravitational anchor. From this central hub, filaments of galaxies stretch outward like spokes on a wheel, with our Milky Way located on a relatively quiet suburban arm. But don't let our modest position fool you. We're caught in Laniakea's flow, just like every other galaxy here, moving at over 600 kilometers per second toward the Great Attractor. This motion isn't just a curiosity, it fundamentally changes how we understand our place in the cosmos. The Hubble expansion tells us the universe is growing, but Laniakea proves that on local scales, gravity still rules supreme, sculpting structures that override cosmic expansion's outward push. What makes Laniakea revolutionary isn't just its scale, it's how this discovery reshuffled our cosmic maps. Before its identification in 2014, astronomers defined superclusters based on galaxy density alone, creating arbitrary borders that often missed the true gravitational relationships between galaxies. Laniakea introduced a radical new approach, mapping the universe by motion rather than static position. Think of it like switching from a flat paper map to a live traffic display. Suddenly, the hidden forces shaping our cosmic neighborhood become visible. Yet even this groundbreaking framework comes with mysteries. The Great Attractor pulling Laniakea's galaxies remains partially obscured by our own galaxy's dusty disk, hiding its true nature. Some suspect it might be the core of an even larger structure, perhaps where multiple superclusters intersect. Others wonder if dark matter plays an unexpected role here, its invisible tendrils guiding galactic motions in ways we can't yet model. One thing's certain, as we peer deeper into Laniakea's structure, we're not just exploring our galactic home, we're deciphering the universe's gravitational language, learning how it writes stories in the motion of galaxies. And here's the humbling twist. Laniakea itself appears to be moving, caught in the gravitational current of an even larger structure called the Shapley supercluster. It's a cosmic Russian nesting doll, each layer revealing how small we truly are in the grand scheme. From our vantage point inside this immeasurable heaven, one truth becomes clear. The universe organizes itself on scales that continually stretch our imagination, forcing us to rethink what it means to be local in an ever-expanding cosmos. Among the countless galaxies dotting the cosmos, Hoag's object stands out like a celestial bullseye, a perfect ring of blue stars encircling a golden core, floating in the void with almost unsettling symmetry. Discovered in 1950 by astronomer Hoag, this peculiar galaxy doesn't just defy expectations, it outright refuses to play by the rules of traditional galaxy formation. Most galaxies come in familiar shapes, spirals with arms winding outward, ellipticals like glowing clouds, or messy irregulars. But Hoag's object, it's a cosmic oddity so rare that for decades, astronomers debated whether it was even a single galaxy or an optical illusion. At first glance, you might mistake it for a collision. After all, ring-shaped galaxies often form when one galaxy punches through another, sending shockwaves that trigger star formation in a circular ripple. But Hoag's object tells a different story. Its pristine ring floats flawlessly around the core, with no signs of distortion or debris to suggest a violent encounter. The gap between the core and the ring is eerily empty, a dark moat separating the two structures. Stranger still, the ring itself rotates at a different speed than the core, as if the two components are dancing to separate rhythms. This isn't the aftermath of a crash, it's a cosmic riddle wrapped in starlight. Theories about its origins range from the plausible to the fantastical. One leading idea suggests a resonance event where gravitational forces aligned gas and stars into this perfect circle over billions of years, like waves organizing pebbles on a beach. Others propose a long-ago interaction with a now-vanished companion galaxy, whose gentle gravitational nudge rather than a direct hit might have sculpted the ring. But the most tantalizing possibility, Hoag's object could be the result of an extremely rare polar ring formation, where a smaller galaxy was shredded and its remains wound around the larger one like ribbon around a maypole. Even more perplexing is what lies beyond Hoag's object itself. Peer closely at images and you'll notice another, fainter ring galaxy lurking in the distant background, almost as if the universe is taunting us with a matched set. This chance alignment deepens the mystery. If such perfect structures can form not once but twice along our line of sight, how many more might be hiding in the cosmic dark? What makes Hoag's object truly revolutionary isn't just its beauty, it's the way it challenges our assumptions about galactic evolution. Textbooks describe galaxy formation as messy and chaotic, full of collisions and mergers. Yet here's a galaxy that appears sculpted with geometric precision, a cosmic artifact that seems too perfect for the turbulent universe we know. Some astronomers now wonder if Hoag's object represents an entirely separate class of galaxies, ones that form through processes we've yet to understand. Perhaps the most humbling lesson of Hoag's object is how much we still don't know. In a universe where we've mapped billions of galaxies, this singular ring reminds us that outliers aren't just curiosities, they're clues, hinting at hidden chapters in the story of how galaxies grow. Every time we encounter something that doesn't fit the mold, it's not a flaw in the cosmos. It's the universe inviting us to look deeper, think differently, and rewrite the rules we thought we knew. Rising from the heart of our galaxy like twin ethereal towers, the Fermi Bubbles are one of the Milky Way's most dramatic hidden features, vast structures of scorching hot gas and high-energy radiation stretching 25,000 light-years above and below the galactic plane. Named after the Fermi Gamma Ray Space Telescope that discovered them in 2010, these colossal formations glow faintly in gamma rays, invisible to human eyes but blazingly clear to our instruments. Picture two titanic hourglasses welded together at their wastes, each lobe pumping out enough energy to power a million supernovae. Yet despite their staggering scale, these bubbles went unnoticed for decades, hidden in plain sight until technology caught up with their subtle, high-energy whisper. What makes the Fermi Bubbles so extraordinary isn't just their size, it's the mystery of their origin. The leading theory suggests they're remnants of an apocalyptic outburst from our galaxy's supermassive black hole, Sagittarius A. Roughly 2 to 4 million years ago, this sleeping giant might have awakened in a feeding frenzy, devouring nearby stars or gas clouds with such violence that it ejected jets of material at nearly the speed of light. These jets, slamming into the gas surrounding the galaxy, could have inflated the bubbles like cosmic balloons, leaving behind a relic of that cataclysm. There's even tantalizing evidence etched into the clouds near the galactic center, a population of young stars moving in suspiciously aligned orbits, as if they formed from the shockwaves of this very explosion. But not all astronomers are convinced. Alternative explanations point to periods of intense star formation in the galactic core, where thousands of massive stars could have collectively exploded as supernova, their combined winds carving out these cavities. Others speculate the bubbles might be signatures of dark matter annihilations, theoretical collisions between invisible particles that would release tremendous bursts of energy. The truth might lie somewhere in between, a complex interplay of astrophysical processes we're only beginning to untangle. One clue comes from the bubble's structure. Unlike the smooth, symmetrical shapes seen in simulations of single explosive events, the Fermi Bubbles show intricate filaments and ridges, suggesting multiple episodes of activity. Their edges are remarkably sharp, as if carved by some cosmic scalpel, and they're filled with ultra-fast moving particles that defy simple explanations. Recent observations have even detected a faint counterpart in X-rays, a halo of million-degree gas that might be the bubble's cooler outer shell. Perhaps most intriguing is what the Fermi Bubbles reveal about our galactic neighborhood. Their very existence suggests the Milky Way isn't the quiet, stable place we once imagined. Like a sleeping dragon occasionally stirring, our galaxy's core seems capable of violent outbursts that reshape its surroundings on staggering scales. If Sagittarius erupted once, it could do so again, a sobering reminder that even our cosmic home isn't immune to celestial upheaval. The bubbles also offer a rare window into the dynamic interplay between galaxies and their central black holes. Across the universe, we see galaxies where these monsters are actively devouring matter, blasting out jets that can outshine every star in their host. The Fermi Bubbles hint that our own black hole might have once belonged to that rowdy crowd before settling into its current quiet phase. They're a fossil record of past fury, a reminder that even the calmest-looking cosmic objects have hidden histories written in bursts of unimaginable energy. And they raise a provocative question. If our mild-mannered Milky Way has such dramatic features lurking in its shadows, what other surprises are waiting to be uncovered in the galaxies beyond? The Fermi Bubbles remind us that the universe rarely fits neatly into categories sometimes. The most extraordinary discoveries come not from peering into the distance, but from looking closer at what we thought we already knew. For billions of years, the Milky Way has spun in serene isolation, but our cosmic solitude is about to end in the most spectacular fashion imaginable. Racing toward us at 250,000 miles per hour, the Andromeda Galaxy, our closest spiral neighbor, is on an inevitable collision course with our own galaxy. This isn't some distant hypothetical. It's a future event etched into the fabric of space-time, set to unfold in roughly 4 billion years. When these two titanic structures meet, they won't just pass by each other, they'll engage in a gravitational dance so colossal it will rearrange the local universe. What makes this impending merger so fascinating isn't just the scale. It's how drastically it contrasts with our usual perception of galaxies as fixed, eternal islands. In reality, galaxies grow and evolve through such collisions, with the Andromeda Milky Way encounter serving as a textbook example of cosmic recycling. As the two spiral giants first approach, their mutual gravity will warp their shapes beyond recognition. Andromeda's disk, currently tilted at an angle from our viewpoint, will loom larger in our night sky as it draws near, its spiral arms stretched and distorted by tidal forces. The Milky Way's familiar band of stars will become increasingly twisted, like a glowing ribbon pulled at both ends. Yet remarkably, direct stellar collisions will be vanishingly rare. Despite each galaxy containing hundreds of billions of stars, the vast distances between them mean most will pass like ships in the night. What will feel the brunt of the impact isn't the stars themselves, it's the gargantuan clouds of gas and dust between them. Compressed by the encounter, these interstellar nurseries will ignite bursts of new star formation, flooding both galaxies with brilliant blue clusters. For a time, the skies of any surviving planets will blaze with unfamiliar constellations as fresh stars ignite across the wreckage. The merger won't be quick. Over billions of years, the two galaxies will swing past each other multiple times in a cosmic game of gravitational tug-of-war, each pass stripping away more of their original structures. Computer simulations reveal the likely outcome. The spiral's delicate disks will shred, their stars scattering into a chaotic, glowing haze. Eventually, their central black holes, Sagittarius, are in the Milky Way, and Andromeda's even more massive counterpart will spiral toward each other, releasing ripples in space-time as they finally merge. What emerges won't resemble either original galaxy. Instead, we'll witness the birth of a new entity, an elliptical galaxy some astronomers have dubbed Milkdromeda, a smooth, featureless orb of stars with no trace of its spiral ancestors. This collision holds profound implications beyond our local group. Galactic mergers are fundamental to how the universe builds its largest structures. The giant ellipticals at the hearts of galaxy clusters, the supposed endpoints of galactic evolution, almost certainly formed through similar ancient mergers. By studying Andromeda's approach, we're glimpsing a universal process in action, one that shaped cosmic history since the first galaxies formed. There's even evidence Andromeda itself is already a product of past mergers. Its outer halo contains stellar streams hinting at smaller galaxies it's consumed. Yet the most startling insight might be how little this upheaval will affect individual star systems. The Sun will likely be flung into a new orbit, but planetary orbits are so small relative to interstellar distances that our solar system could emerge unscathed. Earth's fate hinges more on the Sun's natural evolution than galactic chaos. Our star will have already entered its red giant phase by then. But for any future civilizations witnessing the event, the view will be unforgettable. A night sky where Andromeda dominates first as a distorted wreck, then as the core of a dazzling new galactic metropolis. This inevitable merger forces us to confront how dynamic the universe truly is. We think of cosmic time in terms of billions of years, but from a galactic perspective, collisions like this are routine, the universe's way of reinventing itself. Far from being destructive, such events are creative acts, forging new architectures from old. Andromeda's approach reminds us that even the mightiest structures in space aren't permanent. They're waypoints in an endless cycle of transformation. The galaxies we see today are just snapshots in a much longer story, one where even the Milky Way's identity is fleeting. We've marveled at the visible wonders of the cosmos, the swirling galaxies, glittering star clusters, and colossal superstructures. But what if I told you these breathtaking sights are just the tip of the cosmic iceberg? Beneath them lies an invisible architecture so pervasive it outweighs all visible matter 5-1, the enigmatic dark matter halos. These massive, ghostly spheres envelop every galaxy like cosmic cocoons, their gravitational embrace shaping the universe while remaining utterly imperceptible to our telescopes. The story of dark matter halos begins with a cosmic whodunit. Back in the 1930s, Swiss astronomer Fritz Zwicky noticed something bizarre about the Coma cluster. Its galaxies were moving so fast they should have flown apart, yet something unseen was holding them together. Decades later, Vera Rubin found similar anomalies in spiral galaxies, where stars at the edges rotated just as fast as those near the center, defying Newton's laws unless extra invisible mass was present. These weren't isolated quirks. They pointed to a fundamental truth: galaxies are embedded within vast, unseen spheres of matter that don't interact with light. Modern simulations reveal these halos as intricate webs of dark matter, not smooth clouds, but dynamic structures teeming with subhalos and density fluctuations. Picture a swarm of bees around a hive, where each bee represents a clump of dark matter, collectively forming an invisible framework that dictates how galaxies form and evolve. The Milky Way's own halo stretches nearly 2 million light-years across, 10 times wider than our visible galaxy, containing enough mass to hold thousands of smaller satellite galaxies in orbit. Yet despite its enormity, we only detect it through subtle gravitational tugs on stars and gas. What makes dark matter halos so revolutionary is how they upend our understanding of cosmic structure. Without them, galaxies as we know them couldn't exist. Ordinary matter, the stuff of stars and planets, makes up just 15% of a galaxy's total mass. The rest is this enigmatic halo, whose gravity provides the scaffolding for gas to cool, condense, and eventually ignite into stars. In simulations, when researchers remove dark matter from the equation, galaxies either fail to form or end up as featureless blobs. It's as if the visible universe is merely the decorative icing on an invisible cake. The mystery deepens when we examine how these halos behave. Unlike normal matter, dark matter particles, assuming they exist, barely interact with each other or light. They're cosmic phantoms streaming through Earth and your body right now without a trace. This property creates startling cosmic architecture. Dark matter forms cusps, dense concentrations at galaxy centers, while ordinary matter sinks further inward due to friction. Some halos even exhibit bizarre cores, where density plateaus rather than spikes, challenging our models of how dark matter should clump. Perhaps most intriguing are the discrepancies between prediction and observation. The standard cold dark matter model beautifully replicates large-scale cosmic structure, yet struggles with smaller-scale mysteries, why we find fewer dwarf galaxies orbiting the Milky Way than simulations suggest, or why some galaxies appear too smooth in their dark matter distribution. These puzzles have spawned alternative theories, from warm dark matter, slower-moving particles, to modified gravity frameworks like MIND. Yet none yet explain all the observational quirks without invoking some form of invisible mass. Dark matter halos force us to confront how much of the universe remains hidden. They're the ultimate cosmic puppeteers, shaping galactic collisions, steering star streams, even influencing how galaxies align across billions of light-years. Their discovery humbles us. After centuries of astronomy, we've been studying just the froth on an ocean whose depths we've yet to fathom. Every galaxy we see is really just the glowing signpost to something far grander and more mysterious, an invisible universe waiting to be decoded. And here's the tantalizing part: we may be on the verge of breakthroughs. Experiments like the Large Hadron Collider hunt for hypothetical dark matter particles, while telescopes chart halo shapes through gravitational lensing. Each observation, whether it confirms expectations or defies them, brings us closer to solving one of science's greatest riddles: what exactly is the invisible skeleton holding our cosmos together? Until then, dark matter halos remain both map and mystery, their shadowy presence a constant reminder that reality extends far beyond what our eyes can see. When we think about the brightest objects in the universe, quasars usually top the list, luminous beacons powered by supermassive black holes feasting on gas at the heart of young galaxies. But what happens when these cosmic powerhouses don't just appear as isolated specks in the void, but instead cluster together in groups so vast they stretch the very definition of structure itself? Enter the large quasar groups, sprawling assemblies of these brilliant objects that defy expectations by spanning up to 4 billion light-years across. That's a distance so immense it would take our fastest spacecraft tens of trillions of years to traverse just one of them. Discovered in the early 2000s through painstaking analysis of quasar surveys, these groups aren't just random scatterings, they're organized in coherent patterns, with dozens of quasars aligned in filaments or walls that mirror the universe's large-scale structure, but on steroids. The most famous example, the huge LQG, short for Huge Large Quasar Group, contains 73 quasars spread across a region roughly equivalent to 1/20th of the observable universe's radius. If that sounds unfathomable, it's because it is. The sheer scale of these formations forces astronomers to ask an unsettling question: how could something so enormous emerge in a cosmos supposedly governed by uniformity? This is where the cosmological principle, the idea that, on large scales, the universe should look roughly the same everywhere, starts to wobble. According to standard models, matter should distribute itself evenly across distances beyond a few 100 million light-years, like ink dispersing uniformly through water. Yet large quasar groups laugh in the face of that assumption, presenting clumps of extreme density where there should be smoothness. Some researchers argue these structures might be temporary illusions, chance alignments of quasars at different distances that only appear connected from our vantage point. But statistical analyses suggest the odds of such coincidental groupings are astronomically low, on the order of winning the lottery 100 times in a row. The implications ripple far beyond cosmic cartography. If these groups are real, they might trace the outlines of even larger underlying structures, perhaps titanic filaments of dark matter weaving through the cosmos, funneling gas into pockets dense enough to ignite quasar after quasar during the universe's younger, more volatile epochs. There's also the tantalizing possibility that they're signs of primordial chaos, remnants of density fluctuations from the Big Bang that never fully smoothed out. Imagine the early universe as a pot of simmering soup with some bubbles frozen in time before they could pop. These groups might be the cosmic equivalents preserved for billions of years. Yet for all their grandeur, large quasar groups raise as many questions as answers. Why do they seem more common in certain regions of the sky? Could they be linked to even larger anomalies like the cold spot or the giant arc? And if they truly violate cosmological homogeneity, does that mean we need to revise our fundamental understanding of how the universe organizes itself? Each new quasar survey peels back another layer of this mystery, revealing a cosmos far more complex and far less uniform than we ever anticipated. What's certain is this: these colossal groupings aren't just cosmic curiosities. They're stress tests for our deepest theories, forcing us to confront whether the universe plays by the rules we've set for it. In the end, the large quasar groups might not just be structures. They could be cosmic breadcrumbs leading us toward a new understanding of how everything fits together. Among the countless peculiarities in our cosmic inventory, few are as visually striking or as downright perplexing as the southern ring of galaxies. Discovered in 2023 by a team analyzing data from the Pan-STARRS telescope, this formation isn't just another cluster or filament. It's a near-perfect circle of galaxies spanning an astonishing 1.3 billion light-years across, hovering in the constellation of grooves like a cosmic crown. What makes it extraordinary isn't just its symmetry, though that alone would be rare enough. It's the way this colossal ring exists at all, defying our best models for how matter arranges itself across the universe's largest scales. Picture this, a dozen massive galaxies positioned almost equidistantly along a ring-shaped path, with smaller galaxies sprinkled between them like jewels. If you could view it from above, the structure would resemble a dartboard, an eerie geometric precision that feels almost artificial against the usual cosmic chaos. But the southern ring isn't some optical illusion or projection effect. Spectroscopic measurements confirm these galaxies all lie roughly the same distance from Earth, meaning they're physically linked in three-dimensional space. That's where the mystery deepens. Galactic structures this large typically follow the cosmic web's filamentary pattern, threads of matter intersecting at dense nodes. A closed loop of this scale that wasn't supposed to be possible. Theories about its origins range from the exotic to the revolutionary. One leading hypothesis suggests the ring could be a frozen seismic ripple from the early universe, a relic of the primordial plasma epoch when acoustic waves called baryon acoustic oscillations rippled through the hot, dense cosmos. These waves would have left spherical shells of matter in their wake as they expanded, like bubbles in boiling water. Normally, we see these as statistical peaks in galaxy distributions, not intact rings. If the southern ring is one of these shells preserved in near-perfect form, it would be the largest and cleanest example ever found, a snapshot of the universe's toddler years imprinted on today's galactic landscape. But there's a catch. Simulations predict such rings should be exceedingly rare, so rare that spotting one within our observable universe borders on miraculous. Some astronomers argue this could point to something even stranger, a defect in the fabric of space-time itself. In the early universe, as fundamental forces split apart during cosmic inflation, topological defects might have formed, knots or wrinkles in space that could later seed these bizarre arrangements. Imagine tossing a stone into a pond, only for the ripples to freeze into a permanent ring. That's the kind of cosmic physics we might be dealing with here. What's equally fascinating is how the southern ring challenges our tools for mapping the cosmos. Unlike smaller structures seen in galaxy surveys, this ring scale means it's actually distorted by the expansion of the universe, stretched and reddened in ways that make its true shape harder to discern. Astronomers had to correct for these effects, like straightening a bent photograph to recognize the pattern. It raises a humbling question. If such obvious structures can hide in plain sight, what other colossal shapes might we be missing due to the limitations of our perspective? And then there's the timing. The southern ring's discovery comes just as next-generation telescopes like the Vera Rubin Observatory come online, instruments capable of scanning deeper and wider than ever before. If this ring isn't alone, if it's part of a previously invisible class of megastructures, we might be on the verge of rewriting the cosmic rulebook. Already, some researchers are re-examining older surveys for overlooked patterns, wondering if the southern ring is the first thread in a far grander tapestry. Perhaps the most profound implication lies in what the ring says about chance versus necessity in cosmic architecture. For centuries, we've assumed the universe's large-scale structure emerged from random fluctuations. But perfect circles don't form by accident. They hint at underlying order, at processes we've yet to account for. Whether it's an echo of the Big Bang, a space-time wrinkle, or something entirely new, the Southern Ring doesn't just challenge our models, it invites us to wonder what other symmetries might be woven into the cosmos, waiting for the right moment and the right eyes to uncover them. Deep in the constellation Phoenix, 7 billion light-years from Earth, lurks a cosmic heavyweight so extreme it earned the nickname El Gordo, Spanish for the Fat One. This isn't just another galaxy cluster, it's a blistering, chaotic metropolis of over 2,000 galaxies, weighing in at a staggering 3 million billion times the mass of our Sun. What makes El Gordo truly extraordinary isn't just its size, it's the fact that it exists at all. According to our best models of cosmic evolution, structures this colossal shouldn't have had time to form so early in the universe's history. Yet there it sits, a cosmic rebel breaking all the rules. When astronomers first measured El Gordo's properties using the Hubble Space Telescope and Chandra X-ray Observatory, the data revealed something startling. The cluster's core isn't just dense, it's a cauldron of superheated gas reaching temperatures of 200 million degrees Fahrenheit, hotter than some theoretical models predict should be possible for a cluster this young. To understand why this is so baffling, picture trying to bake a wedding cake in half the usual time. Even with all the right ingredients, physics dictates it needs time to rise properly. El Gordo is that underbaked cake, somehow achieving maturity far quicker than the universe's expansion timeline should allow. The secret to its improbable size might lie in its dramatic birth. El Gordo appears to be the product of two massive galaxy clusters colliding at speeds exceeding 2 million miles per hour. X-ray observations reveal a telltale, bullet-shaped shock wave in its gas, while Hubble's gravitational lensing maps show the cluster's mass split into two distinct clumps, clear evidence of this cosmic pileup. Such mergers aren't rare, but the energy released here is off the charts. During the collision, normal matter got separated from dark matter like cream skimmed from milk, creating a bizarre separation visible in the cluster's structure. Even more intriguing is what El Gordo tells us about dark energy. The cluster's sheer bulk acts as a gravitational lens, warping the light of more distant galaxies into faint arcs, an effect that lets astronomers weigh its dark matter content. These measurements suggest dark energy, the mysterious force accelerating universal expansion, might have been weaker in the past, allowing matter to clump faster than current theories predict. It's as if we've discovered a fossil that contradicts our timeline of evolution, forcing us to reconsider how quickly cosmic structures could grow. But here's the twist: El Gordo might not be alone. Recent surveys have uncovered other massive clusters from this cosmic era, each seemingly too large for their age. Some researchers argue these outliers could hint at exotic physics, perhaps fluctuations in dark energy strength or primordial density, variations we haven't accounted for. Others propose a more radical idea, that our universe contains bubbles where matter clustered unusually fast, making regions like El Gordo the cosmic equivalent of a speed-run glitch. What's undeniable is this cluster's power to reshape our cosmic perspective. By studying its turbulent dynamics, we're glimpsing the universe during its most formative epoch, a time when galaxies assembled into the first great cities of space. El Gordo stands as both a puzzle and a Rosetta Stone, its very existence challenging us to ask, did the early universe play by different rules, or are we just beginning to read the instruction manual? We've mapped the stars, traced the outlines of galaxies, and even peered into the hearts of black holes. Yet the cosmos is still playing a game of hide and seek with one of its most fundamental ingredients. For decades, astronomers faced a glaring puzzle. About half of all the ordinary matter in the universe, the atoms making up planets, stars, and everything we can see, was simply missing. Not dark matter, not some exotic particle, but the very protons and neutrons that should be there, according to our best calculations. This is the missing baryon problem, and its solution lies in the faint, gossamer threads weaving the universe together, the cosmic filaments of the web-like structure spanning the cosmos. These filaments, the largest structures in the universe, are highways of hot, diffuse gas stretching between galaxies and clusters, so tenuous they're nearly invisible. Imagine a spiderweb drenched in fog. Its strands exist, but you'd need the right tools to see them. For the missing matter, that tool turned out to be the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by electrons in these filamentary gases scattering leftover light from the Big Bang. When researchers finally accounted for this signal, they found the missing atoms not in galaxies or stars, but floating in these vast intergalactic rivers, heated to millions of degrees and spread so thin they'd been overlooked. But why does this matter? Beyond completing our cosmic inventory, these filaments hold clues to how the universe organizes itself. They're the scaffolding upon which galaxies are built, funneling gas into the dense nodes where stars ignite. Their study reveals how energy from quasars and supernova pumps through the cosmos, redistributing matter like a celestial circulatory system. More intriguingly, their temperatures and densities don't always match predictions, hinting at gaps in our understanding of feedback mechanisms, how galaxies and their environments influence one another over billions of years. The hunt for missing baryons also forced innovation in observational techniques. X-ray telescopes like Chandra and space observatories like Planck played key roles, but breakthroughs came from combining their data with advanced simulations. Supercomputers now model how gas should clump and flow in these filaments, guiding astronomers to where and how to look. It's a reminder that sometimes, to find what's hidden, we must first teach our instruments to see the universe differently. Yet mysteries linger. Some filaments appear denser or hotter than expected, suggesting additional physics. Perhaps magnetic fields or turbulent energy transfer is at work. Others seem to connect not just galaxies but entire superclusters, raising questions about the true scale of these networks. And while we've accounted for most of the missing baryons, a fraction may still lurk in even more elusive forms. Ultra-diffuse clouds too cold to emit X-rays, or gas trapped in low-density regions beyond current detection limits. What began as a census problem has blossomed into a window on cosmic evolution. These filaments aren't just reservoirs of missing matter, they're active participants in shaping the universe's structure, carrying the raw materials for future galaxies while echoing the processes that forged the first stars. Their discovery didn't just solve a puzzle, it revealed a dynamic, interconnected cosmos far richer than we'd imagined, one where even the emptiest spaces hum with unseen energy, binding everything together in a web we're only beginning to trace. Hidden in the hearts of distant galaxies, megamasers blaze like cosmic lighthouses, not with visible light, but with intense, focused beams of microwave radiation. Unlike their smaller cousins, laser-like masers found in star-forming clouds, these celestial amplifiers pump out microwave emissions millions of times more powerful, often tracing the turbulent orbits of supermassive black holes or the shockwaves of colliding galaxies. The name itself hints at their staggering scale, mega for their immense energy and maser as the microwave equivalent of a laser, a phenomenon where molecules rather than atoms emit synchronized radiation. But what makes these invisible beacons truly remarkable isn't just their luminosity, it's how they've become unexpected tools for mapping the universe's expansion, while simultaneously defying easy explanation. Take the megamaser in galaxy NGC 4258, for example. Nestled around a 23 million solar mass black hole, its microwaves emanate from water molecules swirling at nearly 700 miles per second in an accretion disk just half a light year across. The precision of these emissions is astonishing, like a cosmic ruler etched into space itself. As the microwaves pass through intervening gas clouds, their wavelengths shift in predictable ways, allowing astronomers to calculate distances across hundreds of millions of light years with unprecedented accuracy. In a field where measuring cosmic distances often feels like building a ladder with missing rungs, megamasers provide a crucial, gravity-calibrated step, especially in the Hubble tension debate over conflicting expansion rate measurements. Yet for all their utility, megamasers remain enigmatic. Their formation requires near-perfect conditions, dense molecular gas, an intense energy source, often a black hole's fury or a galaxy merger's chaos, and precise alignment to amplify microwaves along our line of sight. Some galaxies host dozens of megamasers dancing around their cores, while others, seemingly identical in environment, show none at all. Even more puzzling are the rare, orphan megamasers, which flare up in seemingly quiet galactic suburbs far from obvious power sources. One theory suggests these might be echoes of past black hole eruptions, where shockwaves from ancient outbursts excited gas long after the initial violence faded. The real surprise, megamasers might hold keys to understanding galaxy evolution. Their microwaves often trace structures too faint to see directly, like cold gas streams feeding supermassive black holes or the hidden geometry of warped accretion disks. In galaxy UGC 678, a megamaser revealed a tilted, wobbling disk, evidence of a past galactic collision that left the black hole's feeding mechanism permanently askew. Others, like the megamaser in IC 256, show spiral patterns in their microwave emissions, hinting at instabilities that could trigger sudden bursts of black hole activity. Perhaps most tantalizing is their role in probing the early universe. While most known megamasers reside relatively nearby, a handful have been detected at redshifts greater than 0.2, corresponding to light emitted over 2 billion years ago. These distant examples appear more energetic and chaotic than their modern counterparts, as if the universe's younger, more violent epochs produced megamasers on steroids. Could they have been common in the chaotic galactic cores of the early cosmos? And if so, might their faint whispers still linger in deeper surveys, waiting to be uncovered by next-generation radio telescopes like the Square Kilometre Array? What begins as a tool for measurement blossoms into a portal for discovery. Megamasers don't just help us map the universe, they illuminate its hidden physics, from the gravitational whirlpools around black holes to the aftereffects of galactic smash-ups. In their microwave glow, we find both a ruler for the cosmos and a reminder. Sometimes the most profound insights come not from what we see, but from what we learn to listen to. If the universe had a blueprint, dark energy would be the unseen architecture drawing the cosmos on scales so vast. Its influence only becomes apparent when we zoom out to the grandest view. Unlike gravity, which pulls matter together, dark energy operates as a cosmic repulsive force, pushing the universe apart at an ever-increasing rate. And while its effects might seem subtle in our local galactic neighborhood, step back far enough, and you'll see it's weaving the universe into a structure unlike anything we've imagined. The cosmic web, that intricate network of galaxies and voids stretching across billions of light years, isn't just shaped by gravity's pull, it's also being stretched and rearranged by dark energy's relentless push. Picture a spiderweb caught in a gust of wind. Gravity spun the initial threads, but dark energy is the force tugging at the edges, thinning some strands while leaving others oddly intact. This interplay creates a universe where filaments of galaxies grow ever more isolated, their connections strained by the accelerating expansion of space itself. Over time, these threads will stretch to the breaking point, leaving future astronomers in a far lonelier cosmos. What's truly bizarre is how unevenly dark energy's influence plays out. While it dominates the vast voids between galaxy clusters, its effect weakens where matter is densest. In crowded regions like the Laniakea supercluster, gravity still holds sway for now, keeping galaxies bound together even as the space between superclusters expands at breakneck speed. It's like watching a tug of war where one side gets stronger with every passing second. For billions of years, gravity fought to build the cosmic web. Now, dark energy is unraveling it. But here's the twist: dark energy's impact isn't just about expansion. recent simulations suggest it might also be altering the very growth rate of cosmic structures. In a universe without dark energy, superclusters would continue merging into ever larger behemoths. Instead, we're finding evidence that the largest structures like the Hercules-Corona Borealis Great Wall might represent a sort of cosmic ceiling, their growth stunted by dark energy's anti-gravitational effect. It's as if the universe hit pause on building projects beyond a certain scale, freezing these titanic formations in time. Mapping this influence isn't just academic, it's a race against time. As dark energy accelerates the universe's expansion, light from distant galaxies will eventually redshift beyond detectability. Future civilizations might gaze up at a sky where only nearby galaxies remain visible, their view of the cosmic web forever severed. That's why projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are so critical. By measuring how galaxy clustering and cosmic voids evolve across billions of years, we're essentially taking snapshots of dark energy's handiwork in progress. Yet for all we've learned, dark energy remains one of physics' deepest mysteries. Is it a constant force, as Einstein's cosmological constant suggested? Or does its strength vary across space and time, leaving pockets of the universe where expansion behaves differently? Some theories even propose that dark energy could decay or flip in nature, someday switching from repulsion to attraction, collapsing the universe in a big crunch. The cosmic web, as we see it today, is a fleeting moment in an epic saga. Dark energy ensures the universe won't just fade away. It will transform, leaving behind a structure barely recognizable to future observers. And in studying its fingerprints on the grandest scales, we're not just mapping space, we're reading the diary of the universe itself, one stretched and fading page at a time. In the vast tapestry of galaxies, there exists a class of cosmic phantoms so faint they nearly vanish against the blackness of space: ultra-diffuse galaxies. These ghostly structures, spanning sizes comparable to the Milky Way, contain only a fraction of its stars, some with as few as 1% the stellar count. Imagine a city the size of New York, but with streetlights so sparse the entire metropolis appears abandoned. Yet despite their lack of visible matter, these galaxies don't behave as they should. Their stars move at dizzying speeds, hinting at gravitational influences far beyond what their meager starlight can account for. The explanation: these wispy giants are drowning in dark matter, carrying enough of this invisible substance to anchor entire clusters, yet remaining nearly transparent to our telescopes. The discovery of ultra-diffuse galaxies upended assumptions about galactic evolution. Traditional models suggested galaxies needed a critical mass of stars to stay gravitationally bound, otherwise they'd dissipate like smoke in the wind. Yet here are these fragile-seeming structures persisting for billions of years with hardly any stellar glue. Some, like Dragonfly 44 in the Coma cluster, are so rich in dark matter they rival the Milky Way's unseen halo, despite having almost no stars to show for it. It's as if someone took a normal galaxy and erased 99% of its stars, leaving behind a shadowy framework held together by pure mystery. Their origins are even more perplexing. One theory suggests they're failed galaxies, ancient fragments that never accumulated enough gas to spark widespread star formation. Another posits they're the stripped remnants of larger galaxies, their stars ripped away by gravitational encounters while their dark matter cores endured. Then there's the tantalizing possibility that ultra-diffuse galaxies form differently altogether, perhaps in pockets of the universe where dark matter clustered unusually densely, creating gravitational wells too weak to pull in ordinary matter but strong enough to persist across cosmic time. What's most revolutionary is how these galaxies challenge our tools for mapping the cosmos. Too dim to appear in most surveys, they were long overlooked until advances in telescope sensitivity revealed them lurking in plain sight. The Dragonfly telephoto array, designed specifically to detect faint structures, uncovered dozens in the Coma cluster alone, each a pale, sprawling enigma. Some even host globular clusters, dense knots of stars typically found around much larger galaxies, suggesting these ghosts might be the faded remnants of something far grander. Others, like NGC 1052DF2, defy expectations by appearing almost devoid of dark matter altogether, creating a new puzzle for astronomers to unravel. Ultra-diffuse galaxies force us to reconsider the recipe for galactic survival. They prove dark matter doesn't always need stars to sculpt a galaxy. Sometimes it builds invisible scaffolds that linger long after the lights go out. And they whisper a humbling truth: the universe crafts its structures in ways we're only beginning to glimpse, hiding entire cities of shadow where we once saw only void. In their faint glow, we find not just cosmic oddities, but signposts to a deeper understanding of how galaxies, both bright and ghostly, weave the story of the universe. Somewhere in the depths of space, a mysterious signal blasts across the cosmos, an intense burst of radio waves packing more energy than the sun emits in 80 years, yet lasting just milliseconds. These are fast radio bursts, or FRB, some of the universe's most enigmatic signals. First detected in 2007, these flashes appear without warning, vanishing as quickly as they arrive, leaving astronomers scrambling to decode their origins. But the real twist: a handful of these bursts don't just fire once, they repeat, flickering on and off with no discernible pattern, as if some cosmic lighthouse is spinning unpredictably in the dark. The most famous of these repeaters, FRB 1211-2, has become a Rosetta Stone for astronomers. Nestled in a dwarf galaxy 3 billion light-years away, this burst doesn't just echo randomly, it follows an astonishingly precise cycle, flaring up roughly every 157 days like clockwork. Whatever's producing it isn't just some random cataclysm, it's a phenomenon bound by rhythm, hinting at an orbital dance or perhaps the slow buildup and release of energy from an exotic cosmic engine. The leading suspect, a highly magnetized neutron star called a magnetar, locked in a turbulent relationship with a companion star or swirling through a dense nebula. When these ultra-dense stellar corpses experience starquake, sudden shifts in their crust, or when their immensely powerful magnetic fields snap and reconfigure, they might unleash these titanic radio screams across the universe. Yet FRBs aren't just fascinating for what they are, but for what they pass through. As these radio waves race toward Earth, they interact with the diffuse electrons floating in intergalactic space, subtly distorting like light through a prism. This distortion holds clues to the universe's hidden structure, allowing astronomers to measure the otherwise invisible matter strewn between galaxies. It's like using a flashlight beam in a foggy forest. The way the light scatters reveals the density of the mist. Some FRBs even show bizarre, twisted wave patterns, suggesting they've traveled through intensely magnetized environments, possibly near black holes or through the hearts of galaxies. But the plot thickens. In 2020, astronomers got their first break in tracing a non-repeating FRB back to its home, a spiral galaxy surprisingly similar to the Milky Way. This was a shock. Repeaters like FRB 1211-2 tend to originate in messy, star-forming dwarfs where cosmic violence is common. But this one-shot burst came from a calmer, more mature galaxy, forcing scientists to confront an unsettling possibility. There might not be just one type of FRB source, but many. Could neutron star mergers, collapsing black holes, or even, dare we speculate, extraterrestrial technology be producing these signals? The diversity of FRB environments suggests we're dealing with multiple cosmic engines, each capable of unleashing these brilliant, fleeting radio screams. The most tantalizing FRB of all might be the one that shouldn't exist. In 2022, researchers detected a burst emanating from within our own galaxy, and crucially, it was linked to a known magnetar. Finally, a smoking gun, but instead of solving the mystery, this local FRB deepened it. Its properties were subtly different from many distant bursts, lacking the high-energy fingerprint astronomers expected. If some FRBs come from magnetars but others don't, what does that say about the ones still defying explanation? Perhaps the greatest revelation lies in what FRBs are teaching us about the universe's unseen scaffolding. By analyzing how these bursts disperse as they travel, scientists have uncovered a startling deficit of matter compared to theoretical predictions, another twist in the missing baryon problem. It's as if the cosmos is hiding even more of its ordinary matter in places we've yet to fathom, tucked between galaxies in forms we can't easily detect. Every new FRB detection peels back another layer of this mystery. Some pulse with intricate substructure as if encoded with information about their birth. Others arrive with polarization so extreme it suggests they've traversed the most powerful magnetic fields in existence. With each flash, whether it repeats or vanishes forever, these cosmic enigmas remind us that the universe is far from done surprising us. They're not just signals, they're telegrams from the most extreme environments we can imagine, carrying secrets we've only begun to decipher. At the heart of every black hole, according to classical physics, lies a singularity, a point of infinite density where the laws of space and time break down completely. But what if that's not the full story? Enter the Planck star hypothesis, a radical reimagining of black hole interiors that swaps the terrifying singularity for something far stranger, a relic of the original star, frozen at the moment of collapse and compressed to the smallest possible size the universe allows. This idea springs from the fiery marriage of quantum mechanics and general relativity, two theories that famously refuse to play nice when gravity becomes extreme. Instead of collapsing endlessly into a mathematical anomaly, the dying star's matter under this hypothesis rebounds at the Planck scale, the universe's smallest meaningful unit of measurement. Picture a supernova's core squeezed to a sphere just 10 to the negative 35 meters across, smaller than an atom by 20 orders of magnitude. At this incomprehensible density, quantum effects would overwhelm gravity's crush, creating a stable, ultra-dense orb hovering at the threshold of existence. The implications ripple outward. If Planck stars exist, they could explain one of black holes' most puzzling features, their apparent information paradox. Singularities famously destroy information, violating quantum theory's insistence that information can never be truly lost. But a Planck star, with its finite density and quantum structure, might preserve that information like a cosmic hard drive, encoding the history of everything it swallowed in scrambled quantum states on its surface. Here's where it gets wild. Some versions of the theory suggest these stellar remnants aren't static. They could slowly evaporate over eons as Hawking radiation chips away at their mass. This process wouldn't be the slow leak predicted by traditional models, but a delayed explosion with the Planck star's energy releasing in a final, violent burst long after the black hole's formation. Imagine a universe littered with dormant time bombs, remnants of ancient stars waiting to detonate in showers of high-energy particles. Critics argue the theory lacks direct evidence, existing mostly in the realm of mathematical elegance. Yet, tantalizingly, it might leave fingerprints in gravitational wave data. Collisions between black holes could momentarily expose their Planck cores, creating subtle echoes in the ripples of space-time, echoes future observatories like LISA might one day detect. Others speculate that certain high-energy cosmic rays, arriving with unexplainable energies, could be shrapnel from primordial Planck star detonations. What makes the Planck star hypothesis so compelling isn't just its challenge to singularities, it's how it repositions black holes in cosmic history. No longer just destructive maws, they become cosmic archivists, preserving the universe's raw materials in quantum vaults until their eventual rebirth. In this vision, even the darkest objects in space carry the spark of something older, waiting to rewrite their story when the time is right. the universe wasn't always silent. In its first moments, it was a roiling sea of plasma, dense and hot enough to carry sound waves across its entire expanse. These primordial vibrations, echoes of the Big Bang itself, left behind cosmic fingerprints we can still detect today. They're called baryon acoustic oscillations, and they're among the most important clues we have for mapping the universe's hidden skeleton. Picture the early cosmos as a simmering pot of particle soup, with photons and baryons, the ancestors of today's atoms, locked in a relentless push and pull. Gravity would try to clump matter together, while radiation pressure from photons would push it apart. This created rhythmic compressions and rarefactions, essentially sound waves propagating through the infant universe. But when the cosmos cooled enough for atoms to form, an event called recombination, those waves froze in place, leaving spherical shells of matter at a very specific scale, about 500 million light-years apart. Today, these frozen ripples manifest as a subtle preference in galaxy separations. When astronomers chart millions of galaxies, they find a curious statistical excess of pairs separated by that same 500 million light-year distance, the cosmic equivalent of finding all the world's seashells inexplicably spaced exactly 10 paces apart. This isn't random noise, it's the ghostly imprint of those primordial sound waves, preserved for 13.8 billion years like grooves in a cosmic vinyl record. What makes baryon acoustic oscillations revolutionary isn't just their role as a yardstick, though they're arguably the most reliable one we have for measuring cosmic expansion. They also serve as a forensic tool for probing dark energy's influence. By comparing the standard ruler of these oscillations at different cosmic epochs, researchers can track how the universe's expansion rate has changed over time. The results are unequivocal. Dark energy's repulsive force began dominating gravity's pull around 5 billion years ago, accelerating the cosmos toward an increasingly fragmented future. But the story doesn't end there. The oscillations also encode secrets about the universe's composition. Their patterns reveal the balance between dark matter, ordinary matter, and dark energy with precision unmatched by other methods. When combined with cosmic microwave background data, they've helped pin down the universe's total matter content to within just a few percent, confirming that the cosmos is about 5% ordinary matter, 27% dark matter, and 68% dark energy. Perhaps most astonishing is how baryon acoustic oscillations bridge the very large and the very small. The peak separation we observe today originated from quantum fluctuations smaller than an atomic nucleus, stretched to cosmic scales by inflation, the universe's explosive early growth spurt. In these frozen sound waves, we're seeing quantum physics writ large across the heavens, a direct link between the infinitesimal and the infinite, yet mysteries linger. Some measurements suggest slight deviations from the predicted oscillation scale, potential hints of new physics or unforeseen interactions between dark matter and ordinary matter. Others wonder if these patterns might be distorted in unexpected ways by the gravitational lensing of intervening structures or the peculiar motions of galaxies. Each new galaxy survey, from the Sloan Digital Sky Survey to upcoming projects like the Dark Energy Spectroscopic Instrument, delivers sharper views of these cosmic echoes, refining our maps while occasionally introducing new puzzles. In the grand symphony of cosmic structure, baryon acoustic oscillations are both metronome and melody. They set the tempo for the universe's expansion while humming a tune about its birth. And as our observations grow ever more precise, these frozen sound waves continue to whisper secrets about where we came from, what the universe is made of, and perhaps even how it will end. Deep within the Ophiuchus supercluster, some 390 million light-years away, a cosmic catastrophe unfolded with such violence it dwarfs every explosion since the dawn of time, except the Big Bang itself. In 2020, astronomers poring over X-ray data stumbled upon something incomprehensible. a cavity in the hot intergalactic gas so vast it could swallow 15 Milky Ways lined up end to end. This wasn't just another galactic flare, it was the scar of an eruption so powerful it released 5 times more energy than the previous record holder, blasting outward for hundreds of millions of years like a shockwave from the universe's most monstrous detonation. The source of this cataclysm, a supermassive black hole gone berserk at the heart of a galaxy cluster. But this wasn't the typical black hole outburst we've seen elsewhere. The scale defies logic, the energy equivalent of 10 billion gamma-ray bursts unleashed in a single, sustained eruption. Imagine a volcano the size of a solar system erupting for 100 million years straight, spewing jets of plasma at near-light speeds that carved voids into the surrounding cosmos. The sheer force bent magnetic fields into tortured configurations, accelerating particles to energies that make the Large Hadron Collider look like a child's toy. What makes the Ophiuchus eruption so baffling isn't just its energy output, it's the mystery of its trigger. Black holes, even supermassive ones, typically flicker between feeding frenzies and dormancy. But this event suggests something extraordinary. Either an unprecedented galactic collision funneled an entire galaxy's worth of gas into the black hole at once, or we're witnessing a new class of hyper-efficient energy conversion physics at play. Some theorists speculate the black hole's spin crossed a critical threshold, like a cosmic engine redlining, allowing it to extract energy from its rotation with terrifying efficiency. Others wonder if dark matter interactions deep in the cluster's core provided an exotic power source we've yet to comprehend. The aftermath is just as puzzling. Such an explosion should have left the host galaxy cluster disrupted beyond recognition, yet the central galaxy appears strangely intact, as if the eruption somehow bypassed its surroundings like a surgical strike. X-ray observations reveal concentric rings in the gas, like ripples from a stone tossed into a pond, hinting at multiple eruptions spaced over eons. It's as if the black hole has been clearing its throat every few 100 million years, building toward this ultimate outburst. But here's the real kicker: we might be seeing this event in delayed replay. Because light takes time to travel, the eruption actually occurred when Earth was home to nothing more complex than single-celled organisms. By now, the shockwaves have likely faded, leaving behind a quieter but forever altered landscape. Yet the detection of such an event raises a chilling question. If this happened once, could it happen again, perhaps even closer? And what would that mean for any life in its path? The Ophiuchus supercluster eruption forces us to rewrite the textbook on cosmic violence. It proves that black holes, often portrayed as passive vacuum cleaners, can transform into the most destructive engines in existence under the right conditions. More than that, it hints at gaps in our understanding of how energy flows through the universe's largest structures. If something this colossal could hide in plain sight until now, what other ultraviolet phenomena might be lurking in the data, waiting for us to connect the dots? Perhaps most humbling is the timing of its discovery. This record-shattering event wasn't found by some cutting-edge space telescope, but by reanalyzing decades-old observations from the Chandra X-ray Observatory and Rosat with new techniques. The universe had etched its greatest explosion since creation into the sky, and it took us 20 years to notice. That's the paradox of cosmic exploration. Sometimes, the most extraordinary discoveries aren't just about looking deeper into space, but learning how to see what was there all along. We've spent this journey mapping the cosmic structures within our universe, but what if the real frontier lies beyond it? The idea of a multiverse, a vast ensemble of parallel universes, each with their own physical laws, has long been the stuff of theoretical physics and science fiction. Yet recent discoveries suggest these alternate realities might not be entirely hidden. They could be leaving faint fingerprints on the very fabric of our own cosmos, etched into the distribution of galaxies, the anomalies in the cosmic microwave background, and even the voids where nothing seems to exist. Take the cold spot in the CMB, that mysterious, frigid patch we discussed earlier. One of the most radical explanations for its existence isn't something from our universe at all, but the gravitational tug of a neighboring cosmos brushing against ours in the distant past. Think of it like a cosmic hand pressing against a balloon, leaving a temporary indentation that never fully smoothed out. If true, this would mean the cold spot isn't just an anomaly. It's a scar from a collision with another reality, a place where the laws of physics might be utterly alien. The math behind this idea isn't as far-fetched as it sounds. In the multiverse scenario predicted by inflationary cosmology, new universes constantly bud off from one another like bubbles in a boiling pot. Occasionally, these bubbles might graze each other before drifting apart, transferring energy in ways that could imprint irregularities on their surfaces, our universe's CMB being one such surface. Simulations show these collisions would create distinctive patterns, circular asymmetries in temperature, or strange alignments of large-scale structures that defy conventional explanations. The cold spot fits this profile eerily well, though skeptics argue it could still be a statistical fluke, but the multiverse's fingerprints might not just be thermal. Some theorists suggest alternate universes could warp the distribution of dark matter in our own, creating gravitational anomalies that ripple through the cosmic web. Imagine two soap bubbles pressed together. The boundary between them would distort the surface tension, creating invisible ripples. Similarly, a nearby universe's gravity might subtly twist the arrangement of galaxies or amplify the growth of superclusters in ways that leave behind telltale overdensities or strange voids. Projects like the Euclid Space Telescope are now scanning for these distortions, hunting for celestial structures that seem to bend the rules of gravity without a visible cause. Perhaps the wildest possibility involves quantum entanglement, the phenomenon where particles remain mysteriously linked across vast distances. In a multiverse, entangled particles might exist in different universes entirely, their correlated states threading through higher dimensions we can't perceive. If so, the large-scale clustering of matter in our universe could bear traces of this transdimensional interplay, like shadows cast by invisible hands. Already, researchers are probing galaxy surveys for statistical oddities, unexpected correlations or symmetries that might hint at this deeper, hidden connectivity. Of course, not all scientists are convinced. Critics argue that without direct observational evidence, multiverse theories risk becoming untestable speculation. But the allure remains undeniable. If structures like the giant arc or the Hercules-Corona Borealis Great Wall defy conventional cosmology, could they be the first clues that our universe is just one thread in a far grander tapestry? The answer might lie in the next generation of telescopes, poised to map the cosmos with unprecedented precision, not just to study our universe, but to search for the echoes of others. What's at stake isn't just the existence of parallel worlds, but the fundamental nature of reality. If the multiverse leaves scars on our cosmic structures, it would mean the universe isn't a solitary island. It's part of an archipelago with unseen neighbors shaping its shores. And that realization would revolutionize not just cosmology, but our very place in the order of things. Until then, these enigmatic anomalies stand as silent sentinels, guarding the threshold between what we know and what might lie beyond. From the Great Attractor's unseen pull to the eerie perfection of Hoag's object, from the universe-spanning Hercules-Corona Borealis Great Wall to the inexplicable void of the KBC bubble, we've journeyed through 25 cosmic structures that defy expectations, rewrite textbooks, and humble even the most brilliant minds. Each one is a testament to how little we truly know about the vast, strange theater of space we call home. These aren't just astronomical curiosities, they're glaring anomalies that poke holes in our most cherished theories, forcing us to reconsider everything from gravity's grip to the very fabric of reality. Take a step back and the pattern becomes startling. The universe isn't just stranger than we imagined, it's stranger than we can imagine. The Planck star hypothesis redefines black holes as cosmic archivists, not destroyers. The dark flow hints at invisible realms tugging at our galaxy clusters. The Ophiuchus eruption proves black holes can unleash violence beyond comprehension. And the Southern Ring's perfect geometry, it's either a statistical miracle or evidence of physics we've yet to dream of. What binds these discoveries together isn't just their oddity, it's the way they expose the limits of human knowledge. For every question answered, a dozen more arise. Could the cold spot really be a bruise from a parallel universe? Are we living inside a void that skews our cosmic perspective? Does dark energies grip very across the cosmos, weaving structures we're only beginning to trace? The more we explore, the clearer it becomes. We're deciphering the universe with a toddler's alphabet, trying to read Shakespeare in the dark. But here's the thrilling part. These mysteries aren't dead ends, they're invitations. Every anomaly is a clue, every contradiction a doorway. The next revolutionary idea might be hiding in the spin of a megamaser, the whisper of a fast radio burst, or the ghostly glow of an ultra-diffuse galaxy. And with telescopes like JWST and the upcoming Vera Rubin Observatory peeling back layers of the cosmos we've never seen, who knows what else is waiting? So tell us, which of these cosmic enigmas left you awestruck? Where do you think the next breakthrough will come from? The universe is far from done surprising us, and neither are we. If diving into these mysteries left you hungry for more, you're not alone. Hit subscribe because this journey is just beginning. The cosmos has spent 13.8 billion years crafting its greatest riddles. Together, let's uncover what's next.